Lesson 26, again talking about the power series, and we're returning to the concept of does the power series converge, and for what set of values does it converge? What is the radius of convergence? So 6a specifically asks the question, find the radius of convergence, then find the interval of convergence. Okay, so what I'm going to do with this is I'm going to recall the rules that I used for determining if a series was convergent or not. If I saw a factorial and a power of n simultaneously, what rule did I use? I would hope that you use the ratio test. Okay, so that's what I'm going to use here. I'm going to use the ratio test. The limit as n goes to infinity of the absolute value of a to the n plus 1 divided by, so n plus 1 factorial times x to the n plus 1, that thing divided by n factorial times x to the n. Now, if you're quick about this, you'll notice that n plus 1 factorial is really n plus 1 times n factorial. Okay, so this limit will be equal to the limit as n goes to infinity of the absolute value of n plus 1 times n factorial x to the n times x. I'm going to tear one of those away. This is all divided by n factorial times x. The x's cancel, x to the n's cancel out. The n factorials cancel out, and I'm left with this is equaling to the limit as n goes to infinity of n plus 1 absolutely times x, which is really going to be equal to the limit as n goes to infinity of, well, the absolute value of x times n plus 1, because n plus 1 is always a positive number. Well, what does this mean? Well, this means that the absolute value of x has nothing to do with n. Again, the absolute value of x has nothing to do with n, so I can pull that out of the limit. As n goes to infinity of n plus 1, what happens to this? This whole thing goes to infinity. What does that mean? For what x values does this whole thing converge? Well, again, the limit for a ratio test, recall the limit as n goes to infinity of a to the n plus 1 divided by a to the n absolutely has to be less than 1. If it's equal to 1 or anything other, it doesn't converge. What is the only number that I can pick for x that will make this thing to go to a number less than 1? And that's at x equals 0. Okay? So, when does this thing converge? When does this thing converge? By the ratio test, the power series that we have converges at x equals 0. Okay. What's my radius of convergence? 0. It only converges at that given point. If I looked for the interval of convergence, I'd say it's an inclusion of 0 to 0. That's it. There's nothing else. Okay. Now, if I asked for the interval, that's what we would write, because that's the only point that's actually in that interval. So that would be 6a. Okay. Again, notice I looked at the original series and I said, let's use the ratio test. The ratio test says if we're less than 1, we're convergent. I go through all of the values, all of the information here. I simplify it down until I get to the limit of n goes to infinity. So it's infinity times absolute value of x. What x value can I pick that will make that to go to something less than 1? And the only value that I can pick is 0. So by ratio test, power series converges at x equals 0. Only x equals 0. Therefore, the radius is 0. And the interval is 0, 0. Okay? Let's go ahead and look at 6b. Now, 6b looks nasty. Okay? 6b is actually going to be the sum as n equals 0 to infinity of a negative 1 to the power of n, x to the power of 2n plus 1 divided by 2n plus 1 factorial. Now, this particular series is actually a very special one, okay? And we will talk about what it actually is. Okay, we will talk about what it actually is. But before we do that, let's go ahead and actually play with it, okay? Let's talk about what it's doing. Now, how do I determine if this one converges? Well, it's got factorials, it's got power of n, so let's, go back to the nice fallback, the ratio test. Okay, and I told you that I prefer the ratio test. Why? Because it's useful just about everywhere. Remembering the ratio test has the rule of limit a to the n plus 1 over n, a plus n, or a sub n has to be less than 1 for it to converge. So, let's look at the limit as n goes to infinity of this thing such that we have n plus 1 plugged in. So it's negative 1 to the power of n plus 1. Okay. We have x to the power of 2 times n plus 1 plus 1. Again, replacing all of my n's with an n plus 1. I apologize if this is a little bit blurry. This is supposed to be divided by the 2 times the n plus 1 plus 1, all inside the factorial. And that thing is supposed to be divided by this term, just this term, the a sub n. But again, since it's divided by that term, I'm going to flip that term and write this. Okay. Now very carefully, I'm going to start canceling some things out. Negative 1 to the power of n. So I have a negative 1 still left over with that plus 1. Cancel out with this negative 1 to the power of n. Okay. I'm going to rewrite everything else. This is the limit as n goes to infinity of an absolute value of negative 1. That's just 1. So that negative 1 is actually completely unimportant. Okay. So the absolute value of, now this stuff down here is going to be 2n plus 3. 2n plus 3 factorial. So 2n plus 3 factorial times 2n plus 2 factorial times 2n plus 1, and that's where I'm going to stop the factorial. Why? Because I have a 2n plus 1 factorial on top. Okay. Up top here, in terms of the x's, I have 2n plus 2 plus 1, so it's actually going to be x to the power of 2n, okay, plus 1 plus 2 plus 3. 2 more x's. Okay, so x to the power of 2n plus 1 and 2n plus 1 factorial. So now I'm going to cancel out things appropriately. 2n plus 1 factorial, 2n plus 1 factorial. X to the power of 2n plus 1, x to the power of 2n plus 1. What am I left with? This is the limit as n goes to infinity of x squared divided by 2n plus 3, 2n plus 2. Now, tell me, what happens to this thing as n goes to infinity? Well, this is really the same thing as the absolute value of x squared, but the absolute value doesn't really need to be there because x squared is always something positive. And it's going to be of the limit as n goes to infinity. And again, why can I pull this x out here? Because it's got nothing to do with n. X is not part of n. And there's the absolute value of 1 over 2n plus 3 times 2n plus 2. And that whole thing is going to go to 0. So if this whole limit is going to go to 0, this is the absolute value of x squared times 0. Anything times 0 is 0. Wait, 0 is 0. The limit as a sub n over a sub n plus 1 over a sub n, absolute value is less than 1. It converges. This thing, no matter what x value I pick, will converge. Again, this thing, no matter what x value I pick, will converge because it's going to 0. So by the ratio test, okay, by the ratio test, we have convergent on r equals infinity. And my interval of convergence is negative infinity to infinity. Okay, so that actually covers the single point case, okay, from theorem number 4a, and the infinite case, that's theorem 4 part C. We skip over b because we'll come back to it in another example. Let's go ahead and take a look at another example. I'm going to see if I can do the next example all the way down here on this page. We're looking at 6c now. 6c. 6c is the summation as n equals 1 to infinity of x to the n over n. Okay. Now the question is what thing should I use here? What thing should I use here? Well, let's stick to something nice. Let's try that ratio test again. Okay. If this thing is again the limit of a sub n plus 1 over a sub n is less than 1, okay, then I have convergence. So let's take a look at this thing inside that limit. The limit as n goes to infinity of, I'm going to plug in n plus 1 for each of these things. So I'm going to have x to the n plus 1 divided by n plus 1 times, because I'm dividing by this thing, so I'm flipping it, n divided by x to the n. Okay, if that's the case, that means that this limit is actually going to be equal to the limit as n goes to infinity of, the x to the n's cancel out, I have this plus 1 left, so it's just absolute value of x times n divided by n plus 1. But the x doesn't need to be in here, remember. I can pull the x out in terms of an absolute value. So this is the absolute value of x times the limit as n goes to infinity of the absolute value of n over n plus 1. If you want to use L'Hopital's rule, because this top piece goes to infinity, this bottom piece goes to infinity, you can go ahead and make that statement. However, there's another rule that we can utilize. If the powers of the n are the same on top and bottom, it's just going to be the numbers in front of n, so 1 over 1. So this is actually going to be equal to the absolute value of x as this limit goes off to infinity, because this thing goes to a value of 1. Now, when is this thing convergent? Well, when the limit is supposed to be less than 1. There, right in front of you is actually your radius as well as your interval. Okay? My radius is going to be equal to a value of 1, because it's absolutely less than 1. We're bounded. All of our x values are bounded between 1 and a negative 1 on the opposite side. So there's my radius of convergence. What's my interval? Well, I should probably check to see if 1 for x converges, and I should probably see if the negative 1 for x converges, okay? Because the interval could be open on both, it could be closed on both, it could be open on one and closed on the other. So what I'm going to do is I'm going to go ahead and check if x equals 1, what's the series? What is this that I have? It's the series as n equals 1 to infinity of if x is 1, it's 1 to the power of n over n, which is really the summation as n equals 1 to infinity of 1 over n, because it doesn't matter what n is for the power. It doesn't matter what n is for the power if it's just 1 for the number. Wait, this? What series is this? This is the harmonic series. What do I know about the harmonic series? It diverges. So if x equals 1, I have divergent. If x equals 1, I have divergent. So the interval is not going to include that 1 value. I'm going to have the open bracket on 1. Okay. The next thing to do is check what happens at negative 1. The radius is 1 is still valid. It's the issue of the interval is changed. So now I'm going to go ahead and check if x can be equal to a negative 1. Well, if that's the case, that means I have the summation of n equals 1 to infinity of a negative 1 to the power of n divided by n. Wait a second. Isn't this the alternating harmonic series? If this is the alternating harmonic series, then this thing is actually convergent. Okay? We know that because we've done it. I'm not going to go ahead and prove it. If you want to, you're more than welcome to with the alternating series test. Okay? But it is convergent at a negative 1. So my interval of convergence is actually a negative 1 to 1, including the negative 1 value. So the function that this is supposed to approximate, the function that this power series is supposed to approximate, is only accurate between negative 1 and 1. And it's accurate at negative 1, and it's not accurate at 1. Okay? So that there covers all the way through C6. We only have about 2 minutes left in this video, so I'm not going to do 6D. We will come back to that in the next video.